Good morning. Did you know that velocity measurements depend on the frame of reference from which they are taken?
Hey guys.
Hey, Bo.
Hi, Bo.
Flippin' physics.
In other words, the motion of the person taking the measurements will affect the interpretation of the motion of the object being observed.
What?
All right, I'll try again. Let's try showing a classic example. A guy riding a skateboard tosses a ball up in the air. From the perspective or frame of reference of a stationary bystander, the ball appears to follow a parabolic curve. However, from the perspective or frame of reference of the guy moving on the skateboard, the ball appears to move straight up and down. In other words, two observers moving with respect to one another will usually disagree on the description of the motion of an object. To put it one more way, all motion is relative to the observer's viewpoint, or what we call the observer's frame of reference. Thank you very much for learning with me today. I enjoyed learning with you.
Can we please see those again?
Yeah, please.
Sure. I'll add another example, dropping a ball from a moving car.
In this clip, we're going to learn about relative motion. Sometimes a plane will be carried along by the wind and arrive at its destination earlier. Other times there's a headwind that blows against the plane, slowing it down. Sometimes the plane can be blown way off course. Now the pilot's not even aware, maybe. He's flying through the air, he sees clouds in front of him. Meanwhile, the wind is blowing him completely off course. The same thing happens with a boat in water or a swimmer in water. And to understand what's actually happening is a very simple application of vectors. So I'm going to show you what happens in each case, and then I'm going to illustrate it by a little toy car on a treadmill. The treadmill will be like the water or the wind that's blowing, and the car will be like the plane or the boat on water. So here we go. Let's suppose I have a boat, it's still water, and it needs to move to the other side of the river. It heads directly across the river. It has a velocity that is constant. Now, here's a little car, a little motored car, battery operated, about to be placed on a treadmill. The treadmill isn't moving. So it will move directly to the other side at a constant velocity. Here it is in slow motion. It's a similar situation to the river. Now the boat, this time, wants to move across the river. It'll move at the same velocity it did in still water, but the river is carrying it to the right. And we see that the boat is moved off course. Here's what the vectors look like. The boat has the same velocity it would have in still water as it heads directly across the river, and we call that the velocity of the boat relative to the water. We write it like that. The water is now going to carry the boat off to the right. We add them head to tail, these vectors, and this is called velocity of the water relative to the shore. That's how fast somebody on the shore sees it moving. The actual sum now is the vector sum, where I start and where I end, the velocity of the boat relative to the shore. That's what an observer on the shore would see. And notice how I write that, the boat relative to the shore. Well, here's my little car now on the treadmill. And this time, the treadmill will be carrying it off to the right. And the car will be heading with the same velocity it had before across the treadmill. When I add those two vectors, we see that the car, to an observer at the side, would move off at an angle. Here it is. Here it is in slow motion. Now this time, the boat must go across the river, directly across. However, the river is flowing to the right, so which direction should it head? And the answer, it must head against the stream at an angle. And so we add up the velocity of the boat, the velocity of the water, and I get a lesser velocity now across the water. It heads at an angle against the flow of water. Well, that's what happens. It moves across, but at a slower velocity. Now here's my little car on the treadmill, and I want it to head directly across. So the treadmill moves to the right, the car moves into the treadmill at an angle. When I add those two vectors up head to tail, I see that I get a sum that goes directly across the treadmill. So here it is. And here it is in slow motion.